Well, it's hard to believe, but we have come here to the final lecture that we're going to be looking at in physical science this year. So this will be the last video that I will be recording. This is actually going to be a pretty quick one because I think you'll see that sections B or C and D in chapter 18 are pretty self-explanatory. You just actually probably read these pages and get what you need from it. But I'm going to go through this information in rather quick fashion and then do a quick review at the end over the various types of bonds that we've looked at here in this chapter. As a reminder, please make sure you get your tests done and turned into me so that way I can get those graded. And then all that you'll have left is reviewing for the final and then taking the final test, which I'll give more information about that through iGrade. All right, here we go. So we're looking at 18C and D together today. We'll first talk about ionic bonds, and then we'll be talking about metallic bonds. So first of all, forming ionic bonds. Whenever ionic bonds happen, we're talking about elements on the periodic table that have very different electronegativities. Like, for example, sodium, which would be found on the left side of the periodic table, and chlorine, found on the far right side of the periodic table. Whenever these come together to form sodium chloride, notice here that chlorine has an electronegativity of 3.16, whereas sodium has an electronegativity of 0.93. So there is a large difference of electronegativity between chlorine and sodium, which means that this is an ionic bond. And generally between metals and nonmetals, which means the things from the left side of the periodic table with things on the right side. So that's usually where we find the ionic bonds happening, is metals with nonmetals. An electron appears to have transferred from one atom to the other, and the reason why is because, in this case, chlorine wants the electron so much more than sodium does. Sodium is willing to give it up. Chlorine really does want it, and so it's a lot less sharing going on here, but there is no such thing as a purely ionic bond. Remember, in order for it to be a bond, there has to be some amount of sharing of the electron, otherwise they're not bound together. So sodium still has some pull on the electron, but chlorine is really pulling at it a lot more than sodium is. So it's an unequal sharing, a very strongly unequal sharing, but there's still some amount of sharing even in an ionic bond. Just to give you a couple of examples, here's fluorine and sodium, and you'll note that sodium has one electron in its outer energy level. Fluorine has one missing electron in its outer energy level, and so here's a case in which sodium's one dot comes in and fills in to make the 8th dot for fluorine. And so then it kind of looks like this here, where sodium has lost one electron and fluorine has gained it. So you can see the net positive charge on sodium because it lost one electron, but still has the same number of protons in the nucleus. And fluorine, which has picked up an electron, but it still has the same number of protons in the nucleus, is now a net -1 charge. Now, technically, remember, there's still a little bit of sharing, but for all intents and purposes, it's as if fluorine has taken on that electron and sodium has given it up. Magnesium fluoride is another example of this. Note here, in this case, magnesium has 2 electrons in its outermost energy level, and fluorine, again, has 7 in its outer energy level. And so one of those electrons moves over here to that fluorine atom, and then one of them moves over here to this fluorine atom, such that magnesium now has lost 2 electrons, so it's left with a net +2 charge, and each of those fluorines picked up an electron, so they'll have a net -1 charge. Notice here, when you add up across there, it still equals 0. So we haven't lost any electrons ultimately. They're just kind of being transferred from one atom to another. We take sodium sulfide. Again, the same kind of system going on here. Sodium having 1 electron in its outer energy level, and so taking 2 of those sodiums, and sulfur has 2 empty slots. It's got 6 electrons in its outer shell, so those 2 come in and fill in the 2 spots for sulfur, thus giving sulfur a net -2 charge, and each of the sodiums who's given up an electron a net +1 charge. Again, if you add those across, you'll get 0. So no electrons are lost in this procedure. Now, the structure of ionic compounds, they make a structure kind of like a crystal lattice. You can almost think of like Legos or Duplos or building blocks in which they've been built together. If you ever had one of those magnet balls that can kind of like all scrunch together, this is kind of the look of ionic bonded compounds. And they're made up of these unit cells that kind of look like this over here. And you can just start like kind of like building those blocks together, and they just all slot in together and on top of each other, and continue to form the structure of the crystal. So the crystal lattice is made up of these formula units that have been stacked together. That's what an ionic compound looks like. A couple of properties of ionic compounds: they form crystals when they solidify slowly. Most of them have very high melting points, so it means the temperature has to get very, very hot in order to melt ionic substances. Many of them, though, dissolve in water. So if you put them into water, they dissociate, and those ions, which are dissociated when they dissolve in a liquid, forms an electrolyte, which allows electricity to flow through those ions. I think I remember telling you guys that pure water is not a great conductor of electricity. But water, being the universal solvent, dissolves a lot of things. And so it's the particles that are dissolved within water that conduct the electricity. Pure water is not a conductor of electricity, but in most cases, because water dissolves just about everything, there are electrolytes that are sitting in the water, which will conduct the electricity through it. All right, so section D is just on metallic bonds. So metal bonding theory revolves around this idea of the electron C, or free electron theory. The idea here is that metallic bonds with positive metal ions are arranged in a crystal lattice immersed in a sea of negative electrons. And this picture is kind of trying to show that. So you've got these negative electrons that are all kind of, these positive ions are sitting there amidst all of these electrons. What we're trying to do is explain why metals have the properties that they do, because they have very distinctive properties. Valence electrons are free to roam the entire lattice structure, which achieves chemical stability without directly satisfying the octet rule for individual atoms. In other words, these electrons seem to be able to move freely between all of the atoms within the structure. So it doesn't seem like as if they're following any strict octet rule when they're being put together. So you cannot use electron dot notation with metallic bonds. And alloys are just a combination of various metals brought together. And a lot of metals that we deal with are actually alloys, because when different metals are brought together, you are able to get unique properties out of the alloy, thus strengthening or preventing rusting or various things of that nature by adding various metals together into an alloy. So for identical spherical objects, the most efficient arrangement is hexagonal close packed. Alloys are true compounds. Alloys contain a mixture of microcrystals, and you can see some of this being discussed on page 431 of your book. Metals are malleable. Again, I kind of have a picture here with a hammer hitting the top edge of this metal, and note that they can kind of slide over each other. They can be spread out. They're ductile, which means that they can be drawn into thin wires. They conduct electricity well. Remember that electron C allows for those electrons to move freely throughout the lattice structure. And they also conduct heat well, are great conductors of both electricity and heat. And they also provide usually a shiny luster. We're used to this. If we see something kind of shiny with some sort of like reflective qualities, our minds often think that it's something metallic. Now, although we cannot see bonds between atoms, we can often predict the inner structure of an element or compound by observing its properties. So while you might not be able to, with our eyes, be able to see the actual bonds, we can predict some of the inner structure by the properties we observe when considering an element or compound. So at the end of this chapter on page 432, at the bottom of the page, it's a chart, 18-2. You'll see characteristics of bonding types. I think that would be a good thing for you to review in preparation for the test. And I want to give you another review here by just reminding you of these three types of bonds. So first you have the covalent bond, which has distinct molecules held together by intermolecular forces. They have relatively weak attractions, therefore they have low melting points. They are not dense or hard in general, and they are poor conductors of heat and electricity. Network covalent has some exceptions where you see this continuous 3D crystal pattern. Network covalent substances are hard and brittle. They have high melting points and glassy luster. And great examples of this are diamonds and silicates. So just think of a diamond. A diamond is technically, remember, a covalently bonded thing. It's just a bunch of carbon atoms that have been bonded together in a covalent network structure. And so they have some unique properties, these network covalent ones. But otherwise, in general, what we've been talking about in this chapter are just normal covalent molecules. Now, ionic, which we just talked about, have strong bonds. Therefore, they have high melting points and high boiling points. They are typically hard solids. They can be split. They typically are somewhat brittle, so they can be broken apart. They are water soluble. They dissolve in water, and they're great conductors of electricity in water, but not as a solid. So take, for example, sodium chloride, table salt. It's not a good conductor of electricity by itself, but when dissolved in water, it's an incredible electricity. And then last but not least, the metallic bonds. We learned together they carry electrons. They have a luster or shine. They are malleable, which means they can be hammered out and spread out. They're ductile, which means they can be drawn into thin wires. And as we already noted, a mixture of metals is called an alloy. Well, I hope that is helpful. Again, I told you this would be a very, very quick lecture on the second half of Chapter 18. Please reach out to me if you guys need any help at all. Hope that everything is going well and that you finish the rest of this year strong. God bless you guys. Bye-bye.